Alright folks, and welcome to this video lesson. I'm going to take you through the first part of our section 7.5 packet. The section 7.5 is called Logistic Growth, and the part I'm going to show you here concerns partial fractions and using that to integrate various integrands. So it's called partial fraction decomposition, which you saw in pre-calculus, but we're going to see the use for it here in calculus. So copy this down in the top box where it says partial fraction decomposition with distinct linear denominators. And what we're going to say is if you have some function or expression f of x and it's equal to two polynomials divided, or a rational function of p of x over q of x, where p of x and q of x are polynomials, and p of x has a greater degree than q of x. If that's the case, and again the degree of the numerator has to be greater than the degree of the denominator for this to work, then we can rewrite f of x as a sum of rational functions with linear denominators. So the next question becomes, and copy that exactly, but the next question becomes why? Why would we ever want to do this? And it just so happens to be a helpful way of integrating certain kinds of functions. So here's our first example. Alright, so copy that down. What method would you use to integrate here? Your first thought might be U substitution. And if you let u equal the denominator, then you have a du dx of 4x plus 7. But 4x plus 7, it's not really a multiple of the numerator, so it's not going to work out with the cancellation. So U substitution, as a first thought, doesn't seem to work. You might then think, okay, is there a way to do integration by parts? You could split this up into the numerator as one function times the denominator as another, but if you try to do that, let's see, you'd have to make the denominator, that would be x minus 13 times 1 over 2x squared plus 7x plus 3. That's how we consider it two functions multiplied. And so we would want to make this one, we can't integrate on the right. So we'd want to make this our choice for u. Be this guy. I'm just going to put a star there. And we have to make the other one dv. And when we do that, we're going to have u as the star. Du is going to be a pretty messy function. We can take that derivative. We'll have to rewrite it with the power rule and the chain rule, and it's just going to get messier. So then when we go to do our voodoo, integration by parts is voodoo, when we go to do the integral of v du, that part's going to be very messy, and you're not going to be able to do it. You could write it out if you wanted to see what it would look like, but it's not going to work. So integration by parts is rejected because that's not going to be easy here either. However, if we can come up with a clever way to rewrite this fraction, or this rational function, then we can use integration with U substitution. That's where partial fractions comes in. We take this integrand and we say we can rewrite it as something over its first factor. I'm just going to factor this quickly. It's 2x minus 1 and x minus 3. You can check that factoring. But we can rewrite that integrand into a over 2x minus 1 plus b over x minus 3. And if we can solve this for a and b, if we can get constants there, then we will be able to integrate those individual fractions by U substitution. So that's the method of partial fraction decomposition, and we're going to continue this example on the next page. Alright, so here's our setup, and we know this is legitimate from the fact we said earlier about partial fraction decomposition. We know we're going to be able to find some a and b that makes this work. So if you remember, the next step from pre-calculus is we multiply both sides of this equation by this entire denominator. And when you do that, you arrive at x minus 13 equals a, and then the two x minus 1s would cancel out. You'd have x minus 3 plus b, and then the x minus 3s would cancel out, and you have 2x minus 1. And the goal is to solve this for a and b to figure out what these constants are in that numerator. So we do that in two pieces. First we'll solve for a, and then we'll solve for b. The way this method works, there's different ways of showing this. You could set up a system of equations, etc. But the easy way I do it, I actually learned this from Dr. Corley from my college classes. But some people show it differently. The first time I learned it, I did not learn the Corley method. But Corley method, I think, is simpler and straightforward. And the argument is this, since this equation here that I'm pointing to is true for all values of x, we can just let x equal whatever we want. And I'm going to let x equal specific something to make the b go away if I want to solve for a. In other words, I'm going to choose x equal to 1/2 because that's going to make this factor here that I'm underlining 0 out. If x is a half, that part's gone, and then I'm plugging in x is 1/2, and then we have 1/2 minus 13 equals a times, and 1/2 minus 3, that would be negative 5/2. Okay, so we got to do a little fraction math on the side. This is 1/2. 13 over 1 is going to be 26 over 2, so this is going to be negative 25 over 2. And then this is negative 5/2 a. And then I'll multiply both sides by 2/5 to get rid of the good old algebra 1 there. Get rid of the negative 5/2, or negative 2/5 rather. And we do that, we get the 2's cancel out, we have a positive. It looks like a is positive 5. So we found the constant a using the Corley method there. And then I'm going to solve for b in the same fashion. And this way we'll let x equal some number so that this term will 0 out. And we'll let x equal 3. And then solve what's remaining. If x equals 3, then we have 3 minus 13, that's negative 10, equals b times, and then 2x would be times, this would be times 5. 2 times 3 minus 1 is 5. Divide both sides by 5, and we have negative 2 is b. With those two constants, we can now return to our integration using the new form and solve by U substitution. We'll do that on the next slide. Okay, so we can rewrite our original integrand using the partial fraction decomposition, and then we can split it up into two separate integrals that are easily solvable with U substitution. So let's look at 1, we'll look at 2, and then we'll put them together. For 1, notice this can be rewritten as, so I'll put 1 here. This is 5 times the integral of 1 over 2x minus 1 dx. And if we let u equal 2x minus 1, we have du equal to 2. And that's du, so I could put the dx here if I want, but then I want to solve for dx. And that's going to be du over 2. And so we have 5 times the integral of, we have 1 over u, and then dx is equal to du over 2, so I'll bring the over 2 out here, and then du. This gives us 5/2 ln absolute value of u, or 5/2 ln absolute value of 2x minus 1. So that factor is settled. Over to number 2. In a similar way here, you can notice that if you let u equal x minus 3, the du is just 1 dx. So I'm just going to kind of skip a few steps here, but you can see, if you want to write it out, that this just becomes nicely, we could take the negative 2 out, and it's just ln, or natural log, of x minus 3. So this would just become negative 2 log absolute value of x minus 3. Combining that with our other answer, we have minus log of x minus 3. Oh, don't forget the 2. And then in your final answer, you need to have plus c. Okay? In future problems, there may be log properties where you can combine some of these logarithms to rewrite the answer, but this is sufficient for our purposes here. So that's example 1 of how to do partial fraction decomposition and use it to integrate. Thanks for watching this video example, and I'll see you soon.